Okay, shall we start? How's everybody doing? Okay, and today we are going to, as promised, I'm going to talk about 3D point cloud processing, and we are almost reaching the end of the semester. So next week will be the last lecture where today I'm going to talk about 3D point cloud processing, and next week I'm going to talk about neural fields representation. Okay, and yeah, there is also some learning outcomes here. I will start off by talking about what's the definition of implicit and explicit surfaces. So today we are only focusing on one type of representation, that's 3D point cloud representation. And the 3D point cloud representation is actually an explicit representation. Actually, the regular 3D point clouds meshes, they all belong to explicit representation. Okay, and I'll also talk about implicit representation next week. So implicit representation, the sign distance field, and the well-known radiance fields, neural radiance fields, that's NeRF. Okay, that's just one type of representation, one type of implicit representation. I'll define them mathematically today, and then next week we'll look at the different examples, okay, and how we are going to learn them using neural networks. I'll also briefly talk about what are the pros and cons of point cloud representation. Then, of course, this is something that you guys are looking forward to. I will describe how deep learning can be used on 3D point cloud processing. And then once I talk about how I'll introduce PointNet. That's actually the landmark work in 3D point cloud processing by the guy from Stanford University in 2017. And then I will talk about some tasks on 3D point cloud processing, particularly place recognition, key point detection, descriptor, 3D object detector, and then 3D semantic segmentation, point cloud registration, and image to point cloud registration. Okay, so these are several tasks, but it's not limited to just this task. It's just that I'm already exceeding 100 over slides. So I have no more time and energy to go on. There are actually many more tasks in 3D point cloud processing, which actually that we are also researching on. I have several publications on some other tasks, such as point cloud completion or point cloud to dense surfaces completion. So these are the stuff that we are currently still actively working on. Okay, and I'll talk about just these 6 or 7 tasks over here. All right, so nonetheless, even though it's just not limited to this task, I'm already covering quite a number of papers here. Okay, so all today's content is not from any textbook. They are all from the publications and from these top conferences in computer vision and machine learning over the past 5 or 6 years. Okay, they are mostly from the last 3 or 4 years actually. Okay, so it all started from PointNet, this paper here, this landmark paper here, which is actually a very, very simple concept. Okay, we'll look at how this can be done. Then I strongly encourage all of you to look through all the papers after today's lecture. You will probably be able to appreciate more. Okay, because one disclaimer is that I'm just going to touch on the surface of most of them because it's really too much. Okay, I won't go into too much of the detail and I won't prove anything because there are some theorems here, right, in some of these works here. But I won't go too much into those details. I won't also, because this is not a deep learning class, so I'll just assume that you guys already know how to train a deep network. Okay, I'll just talk about the concept and how is it related to 3D. All right, so as I mentioned, that there are 2 types of 3D surface representation, 2 major classes. The first one is what we call the explicit representation, or otherwise known as the parametric representation. Okay, so the second type would be the implicit representation. or otherwise known as the volumetric or volume representation. Okay, so here's some example of the explicit representation. In a discrete form, it could be point cloud, which is what we are going to cover today. And it could also be meshes. So these are essentially just triangular structures, okay, that forms a graph, and it actually helps to define some surfaces. Okay, and it could also be continuous representation, explicit representation. In terms of neural implicit representation would be what we in the discrete form would be boxes or grids, or more commonly, you guys might have heard of this occupancy grid. Okay, so that means that we split the world into a tessellation of regular grids or occupancy regular grids, where each one of these grids will assign a value inside there. It's either 0 or 1. It's either empty or occupied. Okay, but usually we'll just relax this as a range of number from 0 to 1 to indicate whether this the occupancy of that particular grid in the 3D world. And of course, it could also be in continuous form. In the discrete form, it will be occupancy grid. In the continuous form, it will be called the neural fields. Okay, so we'll definitely talk about this next week. The two types of neural fields that is popular right now would be the sine distance function and also the radiance field. Okay, so these are the two types that are interesting right now. Okay, and I also hopefully I will also find some that I will have some time to talk about the most recent papers that links these two together. There are several papers because radiance field you can only do volumetric rendering, and sine distance field you can only do surface rendering, right? But then it would be cool to so most of the earlier works on sine distance field requires the 3D surface for supervision, but radiance field would allow you to render the from one view into another view, so that you can actually use the image itself as a self-supervision. But there are some works that actually tie these two together. That means that you can actually, there are some formulation that allows you to convert SDF into the radiance field, and thus you will be able to render the sine distance field into a novel view for supervision. Okay, there are basically right now there are 3 papers which dominated this conversion here. I will talk about, hopefully I have some time to talk about this, but at least I will cover 1 or 2 of them. Right? Okay, so mathematically, parametric surfaces are defined by a vector value parameterization function. Okay, so this function here is actually mapping a 2D parametric domain represented by omega into a 3D surface represented by S over here. Okay, so this 2D to 3D mapping, it's possible. Okay, since all the 3D surfaces are two manifolds. Okay, so what I meant by two manifold is that regardless of whatever surface that you have, okay, when you are walking on that surface, it's always 2-dimensional only locally, just like Earth. Earth is actually, we are living in a 3D world, but locally, when you stand on Earth, okay, anywhere else, you are actually looking at you are actually on a 2 manifold where everything is you can move everywhere. Okay, so there are some problems with this representation, although intuitively it seems to work. Okay, we'll look at what's the problem next week in more detail. But an intuition is that because the intuition here is that you would always be able to have a 2D domain omega that is living in the R2 space. So if I have some coordinates which I call U and V, whatever coordinates over here, the assumption is that I'm able to always map every single point into a surface. Okay? This is actually a 2 manifold over here. But this assumption might not always be true. and vice versa. So in P2 space, when we look at P2 mapping to P2 mapping, we say that there is or P3 mapping to P3 mapping, we say that there is a homography. When we look at topology like this, we say that there's a homology. Okay, we'll look at it next week. All right, so it's not always true here. Such as, for example, it's impossible to actually map a plane onto a sphere such as Earth. That's why when you unroll the map, the world map, some parts of it are actually distorted. Okay, and examples of this are point clouds. Because when you look at the 3D surfaces on the point cloud, okay, you are actually locally, it's actually a 2D, it's actually a two manifold. Okay, so it's theoretically it should be able to map this. Okay, such and then meshes and also spline surfaces. So you can represent each one of these as using some control points, and then you do a linear combination of it as spline surfaces or Atlas map, which I'm going to most likely talk about next week. All right, so and there's also another major type which is called the implicit or volumetric surface representation. And this is defined to be the zero set of a scalar value function. So on 2D, on 2D, what this means is that, let's say I have a surface over here. Okay, I can easily represent this by either an occupancy grid, okay, occupancy value, or a sign distance value. Sign distance value means that everything here would be zero. Okay, it's a level set or a zero level set over here. Then as you move out from the surface, it's when you're inside the object, it becomes negative. Let's say this is inside the solid, it becomes negative. When you're outside, it becomes positive. Okay, and at any point continuously, okay, the sign distance value here would be the closest distance that you make with the closest surface. Okay, and therefore we are looking at any point that you sample from the 3D world, right? And the surface is defined such that this implicit value is equal to zero. Okay, and examples are occupancy grids, sign distance field, radiance field, or adaptive data structures such as octree. Okay, you can actually represent octree or such that you don't waste space. Okay, I mean, in the 2D space, it will be quad tree. Okay, so you can divide the world into like that means that you have a root, and then every time you go down, there's 4 of this data structure. Okay, let's say all these are empty space, only something here. Then you can further divide it again, right? And then you further divide it into this level. So all the rest you can stop because there's no, you can represent it as one whole empty space here, right? And then this is the top 3. But in the 3D space, you would have a cube, and then you partition it into 8 parts every time, at every level you go. Okay, so that's octree over here. And if you look at these 2 definitions here, mathematically, it also makes sense. Because mathematically, this is really your implicit and explicit functions. Okay, when you talk about implicit functions, right? When you talk about, for example, I didn't include this in the slides, but let's say I talk about a circle, just a 2D circle, right? I can use polar coordinates to represent this. So it will be sine t, cosine t, right? And then t, where t is the angle, and radius, for example. So these are implicit representation, right? Because you're implicitly representing the function. So the function is actually mapping, that function here is directly mapping your input to the surface itself, right? So that's the implicit representation. You can also represent this via x squared plus y squared equals to r squared, okay? Where this is actually an implicit function, right? So you need to solve for the root in order to get the surface, right? That's your zero level set actually, okay? So this is the way that we say implicit and explicit representation is not is not for no reason. It's because mathematically it's as such. Okay. So any question on the 3D representation? I'm giving a very brief introduction to this. Okay. All right. So today we are going to look at just the 3D point cloud in detail, which is a type of explicit representation, as I mentioned. So you can see that why is it explicit representation? Because you this, for example, this torus shape over here, when you walk on the surface, it's actually a two-manifold, it's 2D, but then you are mapping it onto a 3D surface, right? So and the data, so what is we are actually representing every sample. That means that we're sampling from that surface, okay, in terms of a point cloud, a 3D point cloud, okay. And this would be just simply, if you think of it in a more computer science way, okay, this is nothing but just a data structure for 3D representation. And that will be n by 3 matrix, okay, that looks like this. Every point here would be XYZ, okay, and you have n number of points that forms the whole 3D point cloud over here. And but that's nothing stopping you from having a higher dimension representation. That means that you can have the first 3 dimension that represents the spatial coordinate of each point, but you could also have the next D dimension, okay, as any other features that you have. It could be surface normal. That means that I can take any point here and compute the surface normal and then append it to my XYZ. It could also be RGB information. That means that it's a textured point cloud and you can have RGB information on it. You can also include everything. You can have the surface normal as well as the RGB value. Okay, so this D here is up to your imagination. Okay, and the usual data sources that we have for 3D point cloud is usually LiDAR, or LiDAR it's a type of laser sensor. Okay, so what's happening is that it's emitting out laser beams, and then it's measuring the time of flight. Of course, you cannot really measure the time of flight. I mean, you cannot really measure the reflection, and then it's actually over phase shift. Okay, so there is some sensor inside the LiDAR sensor that measures when you are emitting out some laser readings or laser beams onto the, like this thing here, laser beam here. It's reflecting, and there is a phase shift when it's reflected back. Okay, so when you measure this phase shift, you are able to measure what's the distance away from here. Okay, and there's also RGBD camera, as I mentioned in one of the lectures, that your Kinect is actually the RGBD camera. And what it's doing here is that it's actually projecting out certain patterns of infrared light. And then based on the distortion, okay, it's actually measuring what's the shape of or what's the distance away, the depth, of the surface to the camera. Okay, and in fact, one of the very old topic in 3D computer vision, very early 3D computer vision. I think, unfortunately, I don't have time to cover this in the lecture too. But if you are interested, you could actually look at things like shape from shape from X or shape from silhouette. Okay, so this actually talks about how to measure some kind of projection, and then what's the distortion that you can actually infer the 3D shape. All right, it could also be in terms of CAD model. That means that you can actually create it using things like SolidWorks or Pro-E or AutoCAD. Okay, yeah. So CAD model can also help you to create this, but it's usually in the .obj format or apply format. Okay, and you can also sample from these surfaces and to generate a 3D point cloud. And of course, we can also do this by acquire the 3D point cloud by structure for motion, which is what we have already seen previously. Okay, and then and that for images, etc. All right, so some of the important 3D applications of 3D point cloud are land surveying. So you can have terrain. So this is actually part of photogrammetry. A lot of the stuff that we are doing in 3D computer vision are actually stolen from photogrammetry. Okay, so yeah, so land surveying, photogrammetry, urban planning. So if you do things like city planning and so on, you can actually send a drone to map the terrain and do things like this. Or architecture, or you can actually do building and survey the building, or even monitor the integrity, the structural integrity of buildings. Okay. Actually, it can also things like 3D computer vision, not just point cloud, but also what we have learned before, right? In images, it can also be used in all these applications here, right? And I didn't put another one, which I'm actually personally very interested, which is actually forensic science, right? So you can actually use this kind of technology to preserve a crime scene, for example, or to even tell you things that are beyond what you can see, right? So because it's actually picking up all the structural details, right? Or you can use another type of cameras that actually picks up things that you cannot see using the eye. Okay, so this is actually something that I'm always very interested in, like but I have no chance yet to do this in detail. Okay, so you can also do archaeology, preservation of, for example, this is actually the statue David that is carved by Michelangelo. Okay, and this was actually a SIGGRAPH project by Stanford University in 2002 or 3. Okay, they actually took the whole project and then they digitized the whole Michelangelo using this. But nowadays, I think you can just use images and apply NeRF on it. Maybe you can already get that kind of detail. All right, and also metrology, where you do some structural or manufacturing kind of stuff. And yes, also robotics, that you can map the world and then do planning and self-driving on this map on roads. All right, so there are also pros and cons of 3D point cloud. It's not always it's not the ideal case, or it's actually not the only choice, right? So the pros of 3D point cloud is that it has 3D information. There's no depth ambiguity. That means that you know every point in the 3D space. Unlike images where you do structure for motion, but you lose the scale. You don't know how big is the object, unless you know something about the scene. Right? And as well as in terms of coding or in terms of mathematics, this is mathematically simple and concise, because all you need is that you need XYZ for every point, and you can actually represent the surface, any surface, regardless of how complicated or how sophisticated it is. Right? But there are also a bunch of weaknesses for 3D point cloud. First is that it's very sparse. Okay, so even though there is you can have very dense point cloud, it's still sparse compared to meshes, for example, because meshes is just watertight. Okay, and it's also irregular. That means that every point in the there's no structured format to this, so you don't know where is your nearest neighbor, or in order to find the nearest neighbor, it's actually computationally much more expensive than to find the nearest pixel on an image, because pixels in the image, it's actually arranged in a regular tessellation of array. Okay, so you know where's the nearest neighbor, all the 8 neighbors. Okay, but for 3D point cloud, if you want to do this in a very efficient way, probably you would have to use like KD3 or things like this. Okay, I won't talk about what is KV3. I hope all of you know what is a KV3. Okay. In our this assignment?
Yeah.
Oh, really? I can't remember. Okay, good. Good. All right. So good that you know that what's a KV3. It can also be used to do fast search. Okay, there are also libraries that does fast search. There's this fast approximate nearest neighbor library. Okay, but this is irregular. It's nonetheless compared to an image counterpart. It's much more difficult to search. Okay, and there's a lack of textured information because at the rawest form, what it means is that you only have every single point. There's no texture or no RGB information to it. And we'll see that what's interesting about this is that, or what PointNet, which is the next thing that I'm going to talk about, is interesting is that because points are actually unordered. That means that if you take x1, x2, x3, okay, x1, x2, and x3, and you flip it around, you do some permutation. Okay, that's all together. Let's say you only consider 3 points. There are 3 factorial 6 combinations here, right? So you can do x1, x3, x2. They are still going to be the same point cloud. Okay, but this will have some detrimental impact on our deep learning. We'll see why. Okay, and the last problem here, which is we also did some work on this. We had a paper on this, but I'm not going to mention this. That is rotational equivariant and invariance. Okay, so but I'm going to give you some insight behind this. Okay, so let's say I have this chair, it's upright. Okay, I look at different types of chair, they are all upright. And then I train a network that is upright. That network will not be able to work well if I rotate the chair upside down, for example. Okay, because deep networks are not rotationally invariant. CNN itself is translational invariance or equivariant, but it's not rotational invariant. Okay, so and the difference between invariant and equivariance is that invariant means that you take the input upright, you rotate it, it's still going to give you the same result. Okay, equivariance simply means that there is a very deep mathematical formulation. We actually wrote all this in the paper as well. Okay, but I'm just going to give you a very quick insight. Equivariance simply means that if you take this chair, you flip it upside down, the output will also be flipped upside down. You have to undo it, okay, and then it will still match up with the original upright chair. Okay, that's equivariant. Invariant means that you flip it upside down, the output will still be the same as upright. You don't have to do any undoing of the rotation. Okay, but this is a very tough problem. Okay, actually, it's very tough in deep learning. We did something in this direction, and most of the works, we follow most of the works in studying the group theory. Okay, so we actually, because SO3 is actually a group. Okay, and we make use of some group theory to actually study this equivariance and invariance. Okay, but I won't say that we have fully solved the problem. That I also don't think that the problem has been fully solved yet. Okay, nonetheless, I won't go too much into this. All right, so you can also see that LiDAR actually directly gives that it's much more accurate than the image based reconstruction. So the city that it's actually using some LiDAR to map out. I think this is somewhere in Germany. And then here you can see that using structure for motion, the reconstruction is usually less precise. And also you don't get absolute scale from structure for motion. Okay, if you don't know anything about the scene. But for 3D point cloud, you get the absolute scale. Everything is 1-to-1. Okay, the scale. Right. So that's the pro of the advantage of this 3D point cloud. Okay, and so let's look at now, after I define what's the 3D point cloud and the pros and cons, let's just go into how deep learning can be used for this 3D point cloud. So the pioneering work for this is actually PointNet, okay, by this guy, C. et al. From CVPR 2017. So this is a pioneering work, and what it does is that it takes in n/3 point cloud, and then it inputs into the PointNet, and it does three things: classification. So given any point cloud of an object, it's able to tell you the semantic class of that object, and then it's able to also do semantic segmentation of a scene. So this would be, each color here represents a semantic class of the scene. And then it's also able to do part segmentation. This means that given this model of an aeroplane, for example, it's able to tell you where are the wings, where's the body, and where are the tails for the 3D point. But the main problem that this PointNet has to resolve when it's actually taking in point cloud is that for all the neural networks that we know, right, it's MLP or CNN. I'm illustrating here using an MLP, just one neuron, okay? But CNN also works in the same way actually, right? But you can see that they are not permutation invariant. What I meant by not permutation invariant is this, right? So I have a neuron here, which is a function, okay? It's going to, this is just a nonlinear activation. It's a linear mapping followed by a nonlinear activation. So I'm going to represent it as H, and then this would be a nonlinear activation function F, and linear mapping of W transpose X. Okay, you can see that basically what happens here is that let's just take the simplest case. Okay, that the activation function is also linear, it's identity. Okay, so we don't care about it. I'm going to just evaluate the inner term. It becomes this part over here. And you can see that if I were to sort the order, because I have 3 points here, right? I'm going to sort the order from x1, x2, and x3. I'm going to sort into x3, x1, x2. Okay, but they are still the same point. They are still the same point cloud, right? Regardless of how you sort them. In 3D, in the spatial relation, it still remains the same. Nonetheless, you can see that if I were to train the MLP using this way, the weights are actually trained for x1, x2, x3 in this order, right? But if during inference time, if I were to sort the point cloud, even using the same training data, the output is totally different. Okay, so this means that the network is not permutation invariant, and in contrast to our image, you can see that the convolution here, it's always in a order, arranged in a regular order. So there's no such problem for image. Okay, there's no permutation problems in the image counterpart. Okay, and nonetheless, if you look at the point cloud, it's actually orderless. Okay, you look at if I have x1, x2, x3 to xn, n number of points over here, I can arrange them in n factorial combinations. And each one of this combination, it still represents the same point cloud. Brute force way to make it permutation invariant is that you augment the training data with all these n factorial combinations. But each sample that you give, you're going to permutate it n factorial number of times. So this is a silliest way of doing it, because what it means is that you will end up with factorial complexity. That's not good. Okay, so this is not a correct way to do it. So nonetheless, for PointNet, what they propose here is that they propose something that is super simple. Okay, so since it's permutation, since a point cloud is orderless, there's no order to it. Okay, and you want to make the network permutation invariant, then what they do here is that they just treat every point separately, independently. Okay, so if you have n number of points, then I will put each point through an NLP, the same NLP. So these are basically shared NLP, right? I'll put each point inside the same NLP. So I process each one of them independently until I get the final feature here. Okay, so I'll get m by 1024. That means that each point that I have from R3, now I'm mapping it into R1024. Okay, and I have n number of them that goes through the same network. Okay, n times. Okay, but these are all shared weights. That means that there's only one network that goes through here. All right, then finally, you end up with this 1024 dimension, each one of the feature. Then what happens here is that they cleverly use a max pool operation, which is permutation invariant, okay, to get the global feature. Then after that, you do all the semantic segmentation and also classification over here. So there is a proof in the paper, but I'm going to just simplify it into picture like this, okay, into a diagram like this to show you why is it permutation invariant. Because the max pool operation, if you have x1, x2, x3, let's say the max pool operation will be going along the rows and picking up the element that is the maximum among all the inputs, okay? And then you concatenate it into the final output over here. So you can see that if I were to input x1, x2, x3, and x2, x1, x3, my output is still the same, okay? Because I'm taking the max operation, and max operation is regardless of the order, okay? So therefore, because I maintain every feature independently at the beginning, then I do a max pool here, right? Which is permutation invariant. Therefore, the whole thing here is actually permutation invariant. That means that whatever inputs that I give in whichever order, it will still work the same. Okay, it will still work the same way. And that's PointNet. Okay, it's very simple, but he came up with this idea. Now, I think this paper now has been cited like 10,000 times. Okay, and it's a truly nice work, I think. After this work, a lot of people actually started working on Point Cloud. We were one of them. Okay, that actually, when we first saw this paper, we were so excited that we did a lot of the work in this area here. Okay, but one of the although it's nice, there's a limitations of PointNet. Okay, and that limitation is that so if you compare with CNN, okay, CNN has many receptive fields because it's actually convolving the kernel at many layers. Okay, so that means that if you look at one point here at the end, it actually maps back. You are not surprised that it actually maps back to a large patch of the image. So it actually has a very large receptive field, and the larger the receptive field means that you gather more information, and the more powerful your network will be, right? But then if you just look at PointNet, because we are treating every single point independently, and then we just do a max pool at the end. So essentially, there's only one receptive field, okay? And that's all the points. That's not good. That means that it lacks, what it has is this. It has a global knowledge, okay, of the global shape, but then many structures, 3D point cloud, many shapes, okay? It also depends on locally what's the structure, right? So it actually completely ignores this because it treats every single point independently. Okay, it doesn't take into account the neighbors, right? So and there are many papers, and one of them that follow up, which is PointNet++ by the same guy again. Okay, so we also have a paper on this. We call it the SolNet. They came out with this PointNet++ to resolve this because the limitation is that of PointNet is that they treat every single point independently, right? So what this suggests is that let's just do some clustering. Okay, so from the input here, it's going to do some local sampling using the FPF, the furthest point sampling. Then it's doing some k nearest neighbor locally and grouping, and then it's passing through the PointNet for every cluster here. So that means that the point net, although it's independent, it's treating every point independently, it's now treating the cluster, every point inside the cluster independently. Okay, but what it means is that you have the local feature because each point net is local now. And then you end up with a coarser output over here. And we do sampling and grouping again. Okay, so FPS again, and then the k-nearest neighbor again, and we do this. So as a result, this becomes very similar to your multi-layer CNNs. Okay, that means that your hierarchical CNN, and so first we just simply do further point sampling. What it means is that given the set of points, we're going to choose a subset of m points such that each one of the point in the furthest point sampling, okay, they are all it's actually furthest from the rest of the point. Okay, and this is a very standard algorithm in computer graphics actually. And then next for each one of these furthest points, we treat it as the local centroid. Okay, and we find the k nearest neighbor around the neighborhood and cluster it together. Then we put it into the point net. But now each point net here, because we know the cluster, okay, we are going to center it locally with respect to the centroid. That means that I'm going to subtract every point in the cluster with its respective centroid. Okay, then I put it into the point net. And I'm also going to do a multi-resolution grouping. That means that at every layer, okay, I'm going to group this together, and then I'm going to put it into a point net, a local point net. And I get the final output over here. So let's say I have 3 outputs over here. But the final output here, I'm going to take the last layer, the output of the last layer, and concatenate it with the outputs of the first layer. That means that the first 3 points here is all going to be concatenated together. Okay, you can see this something like your skip-link architecture. Okay, the residual or skip-link architecture in ResNet. Okay, so it's actually very similar to that kind of concept. Okay, and so this is the upgrade of the of PointNet into PointNet++. But of course, there are many other variants, okay, to this. And usually, if you now do this kind of work, you would need to cite a whole bunch of papers and to do benchmark against. Okay, this has been very popular for the last 5 years or so. Now, of course, the tide has changed. Okay, now it changes to NeRF. Okay, radiance field, the 3D representation. But point cloud was very popular, and I believe that it's still popular right now. Right now, people are actually looking at how to do self-training representation learning. Okay, so using contrastive loss and all these things. Right. So okay, after defining or introducing you to the two tasks or the two networks that are that have pioneered the point cloud processing, I'm going to next tell you about various point cloud based tasks. Okay, so essentially I'm going to talk about 6 different tasks over here. Okay, the place recognition, key point detector, descriptor, 3D object detection, 3D semantic segmentation, point cloud registration, and image to point cloud registration. So I'm going to introduce you to some of the pioneering work, okay, in all these respective areas over here. Right. So let me talk about the first task, which is point cloud based place recognition. So this is the where am I problem. It's the same as the vocabulary tree that I talked about the last time when I talked about structure for motion. That means that you have a bunch of images. Okay, given one query image, you want to find which one is the most similar one. But now I want to do this. I give you the whole map of the terrain. Okay, this is actually Oxford City. They have a data set from Oxford University. So let's say I give you the whole Oxford City map. These are all 3D point cloud. And then I give you a local 3D point cloud. This means that I'm maybe driving a car or a self-driving car is operating in this city. Okay. But the LiDAR sensor that is mounted onto the car can only see the local view of the scene. Right? So this is the local view. So when I'm building up this map, I happen to tag every part of the point with the GPS coordinate, GPS INS coordinate. Okay. And the question here is that the query point cloud, if I can find where this query point cloud is most similar inside this map, then I would have successfully localized myself. Okay, I would know where am I, right? According to where am I. Let's say this part here, I found out that it's actually this piece over here. Okay, then I would, because this is the reference map, I know the GPS INS coordinates here. So this means that at the end, I'll be able to know what's my coordinate, where am I in the world. Okay, so this is and the where am I problem, it's the most important problem in robotics or navigation. Okay, and so the idea in this paper here, the point is that you can actually create a database of submaps that are geotagged. That means that instead of looking at the whole terrain like this, the whole 3D map point cloud, what I can do is that I can split this into many chunks of submaps. Okay, and each chunk of submap is geo-reference. That means that I know the GPS INS. And then I can downsample it for the sake of efficiency. Okay, because computational efficiency and storage efficiency. Then this is what it will look like after I split this into different chunks, and I'm going to geotag it into using my GPS INS. Then now the question becomes a retrieval problem. Okay, you can see that this query submap is just like your query image, and then your the reference map now becomes chunks of submaps over here, which actually looks like this, one chunk of this, right? So it becomes your database of submaps, or analogously, it becomes something like your database of images where you want to do the retrieval, as what we had mentioned in the structure for motion lecture. All right, so the problem now simply just becomes retrieval. Okay, so in this paper here, this is the first work to actually talk about point cloud retrieval. It's called PointNet VLab because we took PointNet, and then there's another thing called the VLab structure. I'll talk about this very briefly. So the first part here is just PointNet, where we take the point cloud and then we put it into a PointNet, and finally we remove the part of max pool. Okay, so instead of doing max pooling, we replace the max pooling with a more powerful architecture, which is the VLab architecture. And VLab architecture, I will talk about it very briefly. It's actually very similar to the visual words. Okay, so what it's actually doing here is that it's actually learning VLab core. So this is actually all the visual words, the centroid, okay, of the. It looks something like this. Okay, the equation is this here, but this is part of to prove that it's permutation invariant. But then every single, so this is P prime here, where I'm taking all these points here and putting it in, right? So what happens here is that every one of these P prime is going to be assigned to a centroid. This is exactly how the visual words work. Okay, if you still recall, I actually mentioned about this, that we learn the visual words, and then during inference, I'm going to count the frequency. But here, instead of a hard assignment by counting frequency, we're going to do a soft assignment. So this is actually a soft assignment here. It's a softmax function here, right? So WB and the centroids here, which is the visual words, they are all parameters of the deep network. So we are going to learn C, W, and B. Okay, basically, this is the soft assignment. This part here is soft assignment, and then these are all the visual words. So this means that we would have in the end here, the output here would be it's similar to the frequency count, the histogram that we have when we talk about the visual word for image retrieval, right? So if you look at the original, there's basically there's another paper called NetVLab, okay, but that's for that's also published in 2017, I think, or 16, okay, in CVPR. So that paper here basically do image and then propose this VLAB architecture. And then we were the first to actually combine them together and say that this is PointNet VLAB. So today, this is still a popular task although we stopped working on this, right? But it's still a popular task that you still can see occasionally. There are actually almost every conference, you can see papers coming out with new techniques to solve this. And what's interesting here is that we also provide proof that because PointNet uses a softmax to make this part permutation invariant. Okay, but we're replacing it using NetVLab. So NetVLab has to be permutation invariant as well for this to work. Otherwise, it won't work for 3D point cloud because NetVLab was first proposed using images. Okay, then we actually show a very simple proof. So if you have the points that ordered in this way, P1 prime to Pn prime, okay, and we have an output of V, this Vk over here, right? So you have to put it into the soft assignment. So this is the assignment with the centroid, and then you have to sum everything together, right, into K. And what happens here is that because that is a summation, even if I were to permutate this point cloud over here, we can see that basically the sum is permutation invariant. Okay, right? So you will still end up with the same feature at the end, right? So this actually means that it's actually a permutation invariant network. So it shouldn't have any problem working for a 3D point cloud. The way to train this PointNet VLAB would be to use metric distance learning, because we are going to compare the similarity of two features, right? So what happens here is that you would have the same network, the same PointNet VLAB network. Okay, you will repeat it. So we'll have three of this. It's a triplet network. Okay, but they are all the same thing. So we will have an anchor point cloud, a positive point cloud, and a negative point cloud. Okay, and then what happens here is that you know that the positive is the same or roughly taken at the same place as your anchor point cloud. Okay, and what we want here is that we want to create a corpus of training data where we have the positive pair and also a bunch of negative pairs. I know this is, let's say, taken from here, okay, and then this would be my positive pair, okay, and the negative pair would be all the other point clouds that are not taken at the same location, and it better not be the same thing, right? So in this illustration, it's bad because it's actually the same thing, but we actually need to traverse the route a few times. Still remember when we were doing this paper, because we have the car set up with all the LiDARs and all this, a self-driving car actually. So we actually were on the road for like 30 over hours, driving around non-stop 30 over hours to collect all the data sets. Right, around within NUS and also in West Coast. Okay, so so you need to traverse several times the same route, okay, such that the positive pair, it cannot be exactly the same thing, okay, but it has to be taken at the same location over a different time, such that there is some subtle changes or some changes in the point cloud, okay. Otherwise, it won't work. Otherwise, you are just simply overfitting, because if it's exactly the same thing, right, then that loss is always zero. You are not training the network at all. Okay. Yeah. So yes. So that's why we take the positive pair And also the negative pair, it has to be from a different location. Okay? And it can be taken at the same time. That means that it's in the same route, but at a different location. So we have this triplets or tuple of triplets. And then we will, these are the features, P are the features. So we'll propose what we call the lazy triplet loss. Okay. And so the idea here is just this, because the positive pair, when you feed in the positive pair, okay, the output here, the positive feature and the anchor. So these two pairs, they should be as similar as possible. That means that the distance between F plus and FA needs to be minimized. Okay. And the distance between F minus and FA needs to be maximized because they are the negative pair. Okay, so this distance has to be maximized over here. And what you can do is that you can put them into the same function here, okay, such that you maximize it, the positive pair and the negative pair. But if you simply just do this, that can be a trivial solution, okay, because both are outputs of the network. The network can just simply learn everything to be zero, okay. But then that's why you need a alpha here, a margin, and put it into a hinge loss. Hinge loss simply means that it's max of this or zero. Okay, and I'm not going to into a detail, okay, because I'm not teaching deep learning here, right? So, so the ideal case here is this. The ideal case is that when you do a triplet loss, the negative should be the hardest negative, right? So what do I mean by hardest negative? The hardest negative means that there's only one positive, but when you do negative, ideally you should select from all the other samples that are not that anchor, okay? And then you select the one that is closest to the anchor. That's the hardest negative, okay? Because you want to, it's most similar to it, but it's actually not that anchor. You want to push it as far apart as possible. So that's the hardest negative. But the network continuously updated, is continuously updated every iteration in your training. So what it means is that the hardest negative always move around. It always changes. And at every iteration, you cannot just do it at the, because during the training, if you're given a batch, you have to iterate within that batch. Okay, then after that you escape, you need to go back to an epoch and keep on iterating, right? So what it means is that at the final level of iteration, after every iteration, you need to basically search through the whole database of training data in order to get the hardest negative. But this is not good because this is slow, very slow. Okay, but that's the most effective. So we call it lazy triplet because we're just going to take the hardest negative within that batch size. Okay, and it seems to be efficient. There's also a quadruplet loss where you have, because you have the negative, right? When you push the negative apart or pull the positive close to each other, right? You could unknowingly have a third pair that it's supposed to be a negative one, but you could unknowingly push the anchor towards that pair, right? So it's actually then what it suggests is that you just pick the two hardest negative, okay, such that you actually do both concurrently and make sure that they are all pushed apart, okay? And this is the quadruplet loss, but of course it's computationally expensive. And what we are doing here is that we are also searching it for the hardest negative and the second hardest negative in the batch size. Okay, and here's some results that we have where we basically use the Oxford data set, and then this is the university. This data set is actually NUS. Okay, it's actually NUS. Residential area is the West Coast area. Okay, this is actually in One North. Actually, people cite us so many times. They always use this abbreviation in the data set, but nobody knows exactly where it is and what it stands for. Okay, so so we have the training and the test split. Okay, and here's the result. Of course, at that time, we just need to compare to PointNet. Okay, because we were the first to define this task actually. Okay, so before this paper, there's no such task. There's only image retrieval. There's no point cloud retrieval. We were the first to do this. Okay, and then of course at that time it's state of the art. But now I think now we are heavily beaten by like the state of the art. They might have already or saturate the whole thing by a lot. Okay, but what's interesting here is that we unknowingly solve this problem where the same scene, right? If you do a image retrieval, the same scene day and night, and winter versus spring, for example, then you can see that even with our eye here, if I don't tell you that these two are actually the same place, you probably wouldn't be able to find out, right? So vocabulary tree or any form of NetVLAT, the original NetVLAT itself, it will not work under this kind of situation, right? So, but we unknowingly solve this problem using point cloud retrieval. Okay, and so this is cool because structurally it remains the same. But of course, there are also failure cases where you can see that such as this, I query this and I have a wrong match, wrong retrieval, whereas the true match is this. Because what happens is that it's after some time, this car that's parked here, it's actually driven away, right? So there's no more car here. So this is actually the same location, but then you can see that it actually wrongfully retrieved something that is structurally similar. So what this means is that the network is picking up the structure. Okay, it's actually picking out some structure. It's learning the structure of the 3D point cloud as a similarity comparison over here. Okay, any question? Okay, I guess this is kind of straightforward. All right, so let me go into the next task, which is key point detector and descriptor. Okay, so for image-based key point detector and descriptor, I think in your assignment, you might have used SIF feature, right? And SIF descriptor. So image, it's interesting. I mean, you can, because you have texture RGB information, you have RGB information that you can actually use to form the descriptor. So basically, key points are corner points, or key points are stable points in the image, such that when you have a viewpoint change, it won't, you are still able to detect the same stable set of key points. And for each one of the key points, we are going to assign a thumbprint, a signature to it, and that's the descriptor. So in SIF, it's 128 dimension, such that when we have a different viewpoint, we still can detect the same set of key points with the same descriptor, and then we can match it over the image pair here, right? So this would be the image counterpart. But for 3D point cloud, this would be difficult because there's no texture at all, and the point clouds only consists of XYZ input. There were works on learning the descriptors of the key points, but there are not any key point detector works. Okay, the reason is because before us, we were actually the pioneer work to propose key point detector here. Okay, and for 3D point cloud, so using deep learning. But before us, there are some traditional method to do it. But then before that, there's no one actually did it. The primary reason is because you cannot supervise this. Right? There's no full supervision. You cannot, if I give you this point cloud, can you tell me where are the key points? No, right? Even if you can, you are probably not going to label every key point, right? For the full supervision. So before us, nobody actually knew how to do this. Then So the question is how to actually train the network such that it's able to detect the key points. Okay, and so we came up with the what we call the 3D FitNet, and this is actually a weakly supervised triplet network. Okay, that looks like this. Okay, so we are going to use, why is it weakly supervised? Because we only need to know the chunk of subnets, okay, such that it's the same as NetVLATs, point NetVLATs, where we need to know triplets of anchor and a positive pair. That means that this needs to be taken at the same place, okay, but at a different time. Okay, and then we also need to, with the anchor, we need to know where are the negative pair. Okay, so this is the information that we need only to actually train the network to detect key points. Okay, we don't require any labeling at all. So before our 3D FitNet, all the previous work, they use the traditional approach of computing surface normals and all this to get the stable key points. Okay, but we were the first to actually propose this method to use weakly supervision. Okay, and the idea is just this: we give a point cloud, so we do FPS, the furthest point sampling, okay, to randomly sample on the point cloud. Okay, and this FPS is actually inspired by PointNet also uses this, but the original thing that the original place where this algorithm was proposed is actually in computer graphics. Okay, in computer graphics they propose FPS. The reason is because on a surface structure, the furthest point is actually the most representative points of that structure, okay, of the 3D point cloud. So we do furthest point sampling here, and then for each point that we sample, we do clustering. We cluster the k nearest neighbor, okay, and then after that, that we form those clusters, we would dump it into a detector. So this detector here is just a small point net over here. Okay, it's just a point net where at the end here we output two things. One is the attention width, the other one is the orientation. Okay, and so the attention width over here, we'll see that it's actually used to weigh the triplet loss later. But this attention width will also tell us whether this randomly selected cluster here, n by 3, okay, that point over here is a key point or not a key point. Okay, so this is essentially how we actually get the output to tell us whether this is a key point or not a key point. Then orientation, because we have to make it slightly permutation invariant. Okay, because at least locally, we have to make it permutation invariant. So this orientation here will tell us where is the upright direction. So we will learn this using the point cloud. This is the detector part. We will also have the descriptor part. Okay, this is just something like a thumbprint for each one of the key points that we are learning. And we'll just put this orientation into the cluster so that we can rotate it upright. Okay, and then this is also something like a point net here. There's a max pooling, and we concatenate it together. So finally, it will output a descriptor over here. So this descriptor, we will have one descriptor per cluster, okay, in all the positive, anchor, and negative pair. Then finally, once we have this, we will put it through a similarity matrix that looks like this. Okay, so what happens here is that the anchor here, it will go into each row of this, okay, in these two matrices over here. Then the positive point cloud will come in here. So each entry here would be the positive distance and between the anchor and the positive point cloud. Okay, so what happens here is that for each row, we are going to take the minimum distance. Okay, this means that between the positive anchor, I'm going to, for each one of my potential key point or descriptor in my each one of the key point in the anchor, I'm going to take the closest one that is from my positive pair. Okay, and this will give me my final loss here. So I'm going to sum this, and this will be the distance. Okay, it's the closest match. Similarly, between the anchor and the negative, I'm also going to take the closest match over here. Okay, it's also the minimum. But instead of minimizing it, which is because this positive and anchor, they are supposed to be a match. They are from the same area. So the descriptors that we take, it better be the minimum, the closest one. It better be minimized. I want it to be as close as possible. But I'm also going to take the minimum over here. This forms my hardest negative between the anchor and the negative. So I want to maximize it. So I take minus of this distance over here. Okay, and then I dump everything into a triplet, a marginal loss or a hinge loss here. Then, and finally, what happens here is that I'm going to weigh this with my weights that I have found over here. I'm going to normalize this. Okay, then I'm going to weigh this with W prime over here. So this attention will tell me whether this key point is significant or not, whether it should be a key point or not. Okay, if it is not a key point, then I should reduce this, right? So in the end, we learn this, right? Using the same, actually the same data set that from PointNet VLab, and we can see that. So basically, before us, there's no. Our key point is this 3D FinNet key point, and then all these key points that are existing, ISS, RS, or RSTF, they are all standard geometrical approaches because we are the first to learn this using deep learning, and we can see that we actually outperform all of them, right? So if we compare, we can see that this attention that we have learned, it's actually the more yellow, the brighter it is, the higher the attention. You can see that it's actually focusing all on the structural, meaningful places. But on the road, for example, there's nothing because it's flat. Okay, so our focus is really not there, right? And then the key point that's obtained here is all on the structural, interesting places. Whereas, look at ISS, the standard conventional approach, you can see that there are many false positives on the road, which is not meaningful at all. Yeah, so we published this at ECCV 2018. Yeah, of course, at that time, we no need to compare with any other deep learning methods because we are the first. But for descriptors, there are many other methods already at that time. So there's 3D match, there's CGF, FPFH, I think is also a deep learning method if I didn't remember wrongly. So all these are a lot of deep learning methods over here. Then we are the first to actually come out with this, or to couple them together. Actually, we do both simultaneously, right? Then, but we are not satisfied with this. So later on, we came up with the second approach because this is weakly supervised. Then we thought that we might as well do away with the INS and GPS. We do it fully self-supervised. Right? So yeah, see some of the results. So we do unsupervised learning, okay, in the next work, which is the next year. In 2019 ICCV, we did this. So the idea here is that this is just for key point detection. Okay, we do a unsupervised key point detection, stable key point detection, and what we want to do is that given we will just design a network to do training without any labels of the key points, as well as we won't do any labeling of where the key point is taken, okay, as compared to the previous one. We'll just take that, any key point, any set of point cloud, and do self-supervised learning on it. Okay, so nowadays, has become quite a norm already. Like people will do contrastive learning, where they augment the same data, they rotate it or whatever, then they do some form of augmentation. But at that time, we were also one of the first to actually use this kind of idea. So given a point cloud here, right? What we do here is that we are going to randomly choose generate a transformation and transform this into x from x here, transform it to an x tilde. Then we put it into the feature proposer network, which is this guy over here. Okay, it's kind of complicated, but then I think there are many points. There are actually this was taken. This was actually done or inspired by SONET. Okay, at that time we thought of this, and then so the feature proposer network, and then the output here would be that from the original point cloud, I will get a set of key points. Okay, I'll talk about what sigma later. Sigma is just the uncertainty, and it acts as the same as the attention that we saw earlier, the uncertainty. Okay, and then for when it's rotated or transformed, I would have another set of Q tilde that is here. So the key points here. So when you undo this, okay, when you undo this Q tilde via T inverse over here, so this T inverse, then the two sets of key points should match up. Okay, and then this means that it can be fully self-supervised. But I didn't show what I didn't show in this slides here. We did some proof in a formal proof actually in the paper to show that actually if you do this, just naively do something like this, right? That's a degenerate case, because you can actually learn the centroid or learn anywhere in the principal axis, and no matter how you transform it, you will still get the same point. All right, so but we found a very trivial solution to this. So you just limit the receptive field. As you limit because what happens here is that we found out that if you don't limit the receptive field, that means that the network has a global knowledge of the shape of the point, and the centroid and the principal axis are actually very good representation of the global information. So it can actually degenerate. We also show experimentally it does degenerate to that if we widen the receptive field. So you have to select a narrow enough receptive field such that it's not sufficient to degenerate into the principal axis, okay, or centroid, but it's still able to give us meaningful outputs over here, and it does work quite well here. Okay, so a straightforward way is that Q and Q point, we just take the chamfer law. Okay, but then if we just do this is a hard assignment. It's not meaningful, okay, or it's not equally. We know that the M proposers here from the feature proposer network, they are not going to be equally salient. Okay, so they are not going to be equally salient. So the receptive field here can be featureless surface. Okay, and so what we propose here is that we also output sigma, which is the uncertainty. You can see as an uncertainty. So we put it into exponential distribution here, such that when we minimize this, it's actually characterized by a distribution instead of a hard assignment. Okay, so this sigma here, since it's also learned, okay, but there's no need for any supervision. The supervision is actually to minimize this log likelihood here. Okay, so together with the sigma here is just the output. Okay, so if you do this, then we realize that actually the sigma will measure the uncertainty. Okay, and it's telling us how likely or how salient that particular point is for as a feature. Okay, so then we also so one way that you can do the feature, okay, the key point, which is actually in our 3D FitNet. Okay, in 3D FitNet, we just propose the key point using one of the points in the point cloud. But the key point need not necessarily be from one of the points, right? Because you are representing a surface, a continuous surface, and the key points are just samples on the surface. So it could be somewhere in between actually, right? But then if you force that key point to be on the on one of the samples of the point cloud, then you are subjecting the whole thing to quantization error, right? So because you are quantizing, I mean, when you draw samples of points from the surface, this is a form of quantization, right? So we would be subjected to quantization error. And therefore, we say that, let's not constrain the feature proposal network. We'll just let it output any point in the 3D space. Okay. But if you just do this, then that 3D point might be very far off. It might be floating away. So we enforce the point-to-point loss. That means that whatever that we output, it should be the distance, the chamfer distance to the closest point should be minimized. Okay, so we don't force the output to be one of the points in the point cloud, but we force it to be close to the point cloud itself. Okay, and here's if we have the point-to-point loss, it's actually all very close to the surface. Okay, and then if we don't have it, you can see that they are all floating around. Okay, so this is the whole idea here, and it turns out that this works far better than the in terms of repeatability. Okay, it works far better than our own work, 3D FitNet. Okay, because this 3D FitNet was published at ECCV 2018. This work was published at ICCV 2019. Yeah, so but we were the second work, okay, to compare with ourselves. That's the 3D PointNet, 3D FitNet. Okay, and then you can see that actually in terms of repeatability, it beats everything by a huge margin here, even though it's self-supervised. Okay, and here's some other results. We call this method the USIP. It stands for unsupervised interest point, stable interest point. Okay, and yeah, so you can see that all this after registration is very stable. All right, any question up to this point? If not, then let me talk about the next task, which is 3D object detection. Okay, so the task is this. The objective is just this, given the 3D input point cloud, okay, that looks like this. And then what I want to do here is that I want to detect where are the objects, okay, and put the tightest bounding box around each object. Okay, so I want to put the tightest bounding box that's parameterized by 7 parameters. So XYZ, which is the center of the bounding box, HWL is height, width, length of the tightest bounding box, as well as we always assume that it's upright. Okay, so there's only a yaw angle, which is theta. Okay, and that's the heading. So this is what we want to assign, as well as around each object and its okay, as well as the semantic class of each of the bounding box. Okay, so this is the task of a 3D object detection. It's much more difficult than the 2D object detection counterpart. Okay, although there are many methods already in 2D object detection, like FASTA, CNN, things like this. I think the latest state of the art is DETER, okay, using transformer. Yeah, using transformer, right? So the visual transform, the 16 by 16 transform. So things like this already, but 3D object detection is much more difficult because you have very sparse point cloud. And some of the objects, right, you can see that because of the our perception. So if you use a laser sensor or you use a RGBD camera, right, we're all subjected to what we call the A-model perception. So A-model perception means that when I look at you, I cannot see what's behind you. Okay, I only see what's in front of you. And when I look at this from this point of view, I only see the front part of the chair that is in my view, but the back I don't see at all. There's no points at the. You will basically cast a shadow on anything that is behind, right? So that's the difficult part of when you do 3D object detection, that is the main difficulty there. Okay, and then this guy, the same guy who proposed PointNet, he came up with the this VoteNet. Okay, it was one of the first work in 3D object detection. It's pretty cool, this work. So the idea is very simple. Okay, the idea is that I give you this 3D point cloud. Okay, it's actually generating votes to the object center. So it first generates a set of seeds. Then in each seeds, it's actually casting a vote, okay, that points towards the object center, the closest object center. Then what we do is that we aggregate those votes. And then finally, each vote also contains a feature. Then finally, it uses that aggregated feature to regress for the bounding box. Okay, so 3D object detection is challenging because it's both a regression and a detection problem. Okay, the reason is because this part here is regression, and this part here is classification. Okay, classification is easier than regression. That's why I won't talk about the details of the losses, but the detail of the losses here is actually greatly inspired by the line of works in like fast RCNN, faster RCNN kind of work, where you would need to do anchor box, right? So basically you have a proposal and then you actually subtract from the anchor or from the proposal, because deep network also has a problem when you are going to ask it to predict unbounded numbers. Let's say in this 3D scene, if I just tell the network to say that predict a bounding box, given that point cloud of all the chairs, out of nowhere, right, you ask it to regress XYZ, all these 7 parameters that are not bounded at all, right? Because it basically ranges from -infinity to infinity. Then deep network is very poor at doing this. That's why the idea of anchor boxes, right? So you treat it as like you discretize the whole space into anchor boxes. Actually, faster RCNN, just for every point you have 9 anchor boxes. Then you actually check what is deviation. What is the deviation? And this becomes relative instead of absolute, right? So deep networks are better at doing this, because when you do relative, it becomes more bounded in a bounded space, right? And the room margin for error is actually better. So probably you would have learned all this in the deep learning classes, because all these are classic in deep learning, right? So yes, they use the same thing, right? But in 3D object detection, there is an additional challenge, which is amodality, okay, because you see only parts of the object. But whereas compared to the 2D counterpart image, you see everything, it's dense. Although the amodality perception also exists, it's not so severe there because you are just putting a 2D bounding box. Okay, the parameter is far lower than this. All right, so the idea here is this. So VoteNet looks like this. Okay, so the first part here is the voting for is a seed to generate seed. For input point cloud, you generate a set of seeds. Then for each seeds, you generate you cast a vote. So basically, you output what is the delta distance from every point, every seed here to the nearest object center. Okay, so these are the illustration of the after you point those objects, delta distance to the object center. Then finally we cluster the vote, and then that is of a certain nearest neighbor away. Then we use these votes to regress for the output here. Okay, so these are your proposals actually. Once you have your proposals, the regression would be more or less anchored at a certain part. So here are some details. For the input points, we just use PointNet++ to generate M seeds. okay, and plus a feature. Okay, so you still have the XYZ of the location of the seats, and then plus a feature that we learned from a C-dimensional feature. Then after that, we do half voting with the deep network. Okay, so what it means is that I have the seat, m number of seats here. Then I'm going to, for each seat, I have the seat location, XYZ, as well as a feature that's learned from PointNet++. And then I will use a MLP to take in F and output a delta X, such that Y equals to delta X plus delta X is because I have a seat, okay, I'm going to plus delta X, and this part here is Y. So this is delta X and this is X. So this Y here would be the object center, okay, would be pointing towards the object center. As well as I'm going to generate a delta F such that I have a new feature, which I call G. Okay, so these are the votes that I'm going to generate. And I'm going to supervise this delta, okay, because I have the ground truth, right? So I'm going to supervise this such that the delta I can compute and then have a vote regularization loss here. And this is supposed to be this. What happens here is that for the set of votes, okay, I'm going to, because I have n number of votes here, I'm going to sample k votes, which is k subset. Okay, using the FPF, I'm going to use the furthest point sampling to get the k number of votes. Then I'm going to form k clusters. Okay, so each one of these k votes that I selected using further sample point, I'm going to use it as a centroid, and then find all those points that are within a radius of R, all those other votes that are within radius of R from it. Okay, then this will form my k cluster. And so given the k clusters, okay, all these given a k cluster, that means that I have k number of clusters now, and each cluster there will be all the votes inside there. Now suppose I'm looking at one cluster where all the votes inside there, I'm going to now call it W. Then I equals to 1 to n, where I have the W is actually the vote center, the spatial location, and the vote feature. Okay, and I'm going to now center it with respect to the centroid. Okay, because I can compute the centroid here. Inside the cluster, I have all the spatial location. I can compute the centroid, which I'm going to call Zj here. Then I can actually centralize it divided by the radius, because I'm selecting it based on the radius here. So I will take it as Z prime to make it local. Okay. Then finally, I'm going to put these votes, okay, all these votes into a MLP. And I'm going to 2 layers of MLP here. Okay. And finally, the output will be just a P vector, m-dimensional vector, where this P vector here is the objectness score. That means that it's 0 to 1. Closer to 1 means that there is an object there. If it is 0, there's no object. Then I'll ignore all the parameters. It doesn't matter anymore, right? Then if there's an object, it will in P here, it will also output my bounding box parameters and the semantic classification score. So note that the way that they parameterize this is this, that because now I have all these Z already, I know where are the votes, right? So the bounding box parameters are all parameterized with respect to these votes. Okay, so that means that you don't have to predict. You will never predict the absolute coordinates. Okay, otherwise it's unbounded, right? So and also the semantic classification score. So these are all. I didn't write down the loss function, but the loss function here are all. Since this is it's just a cost entropy. Okay, and then this bounding box here is a regression loss, but anchored around the ground truth. So you are actually predicting just the delta, or you are actually supervising the delta away from the ground truth. Okay, so here's the result. Of course, they show the best result. Yeah, any question? So this is all for the VoteNet. It's a very useful framework. I think up to today is still one of the best. If I'm not wrong, there's another one which is the 3D transformer. I think is using it's 3D Deter, if I didn't remember wrongly. Okay, that is based on 2D. I mean Deter for 2D object detection, and it seems to perform better than VoteNet. But otherwise, VoteNet is also not that worse. Not that much worse. It still remains the one of the most powerful 3D object detector up to now. Okay, yes. Oh, of course, you need to weigh, right? I mean, if you have different objectives in different scale, you need to weigh. It's very important. It's very important. So the thing is that let's say you have two objective functions. Okay? If my objective function is just in one dimension, that means I only have one variable, and this is my cost, right? My objective function. Let's say I have L1 and L2, and if L1 is if L1 is of this scale and L2 is of this scale, then you better scale up L2 to be the same as L1. Otherwise, you are not going to meet both objectives. Right? You are forever optimizing just the dominant one. Okay, this is important. All right, unless you know that both. So one of the important thing, like when it's not just deep learning, but also in general optimization in so in computer vision, especially 3D computer vision, because you can actually be optimizing in the 3D space. So if you have a point cloud, you optimize in a 3D space. Then when you project it back onto the pixel, you minimize those errors on a pixel space, right? Pixel space is there's no dimension, it's unitless, right? So you just know how many pixels away. But in 3D space, there might be metric distance. Then if you are going to optimize both together, one is in the 3D space, one is in the pixel space. Obviously, they don't live in the same world. So you cannot optimize them together like that. You have to scale it. Okay. Any other question? All right, if no other question, then let's go for a 5 minutes break. Okay, shall we continue and then try to finish everything? All right, so the next task that I'm talking about, I will talk about is 3D semantic segmentation. So the idea here is that for each point cloud here, for each point in the point cloud, I want to label one of k classes. Okay, so this is the most naive way of semantic segmentation, semantic labeling. Because now there are more sophisticated definitions of this, like panoptic segmentation, instance segmentation, and all this, and which requires because basically we don't differentiate. The naive way of doing segmentation here, we don't differentiate between different instances. Like for example, if I have a chair class or books, for example, then I will just label every book as that in that class. I don't differentiate between different instances of books. Okay, so instance segmentation does that, and then there's also panoptic segmentation, where basically panoptic segmentation is just instance segmentation, but anything that's in the background that you cannot have the final definition into instances, you just let it remain as segmentation. Okay, so this 3D segmentation, there are many works in the early days of when this PointNet was introduced, right? That so many that I forgot which one is actually the most significant one, right? Because I was actually putting all the slides together only yesterday, and that's why it was a last minute thing. That I mean, I should have done it better to try to recall which is the most significant, the earliest work. Then in the end, I did it last minute, so I decided that instead of finding the most significant work in the fully supervised one, I'll tell you which is the most significant work in the non or weekly supervised one. Okay, this is actually the first work for week supervision, weekly supervised learning in 3D semantic segmentation. Because when you do segmentation in 3D, compared to 2D images, it's actually a lot more tedious to label in 3D. So suppose I give you a point cloud that looks like this, okay, or looks like this. I ask you to go and label every point. This is actually kind of tedious compared to an image. An image is already tedious, but at least it's just an array. It's on the plane, right? You can actually ask anyone to go and label it. And to an untrained eye, that means that if you don't look at point cloud very frequently, actually our eyes are not accustomed to. We are not meant to look at point cloud. Okay, we are more looking at so in terms of like deep learning, right? When you look at different layers of deep learning, because they discovered that at different layer, you are looking at the finest feature, lowest level feature, and then subsequently higher level feature. Right? So at some level, it's the lines and curves and contours. Right? So actually, human eye actually function at that level. We are better in terms of looking at the contours rather than the point cloud. So it's actually very difficult to label using, to go and do this kind of tedious job of labeling every point. Okay, so for 3D shape segmentation, the problem is that you need 1K to 10K points of label. And it's even worse for indoor scene segmentation. You can, it drastically change to millions of points that you need to label for every scene. So it's kind of tedious to do that. Therefore, actually, this was also the first, this was the first work that we proposed, okay, in 2020 to do with supervision in the semantic point cloud labeling. So we discovered that actually by doing even full supervision is 100% labeled, and then sorry, sidetrack a little bit. You know why we decided to do this? Okay, besides the whole idea of it's really genuinely very tedious to label large amounts of training data, right? So it actually makes more sense to reduce this and such that you can actually make use of unlabeled data as well, because there is a lot of unlabeled data in the wild. So we can easily collect all this data, right? And yeah, so and nowadays people are also looking at how to use synthetic data. So synthetic to real. There's actually a domain shift. Yeah, that's why we came up with this weekly supervised. So instead of having a full labeled training data, we only have a few points. And to the extent that we discovered that even just 1 point, right, is sufficient, right, per semantic class. As long as it's continuous, so 1 point is actually sufficient in our framework. So basically, it consists of 4 components inside here, right? Of course, there is this component of feature extraction. So from a point cloud, we augment it, and then this is just by random flipping, rotation, and so on, right? And then we have the same encoder network that gives the features of the point cloud. And we would have an incomplete supervision branch, because this is we only have weak labels, because weekly supervised. That means that we have incomplete labels, very sparsely labeled. And here, what we do here is that we will just add a mask. All those with labels, we will have the mask of 1, and all those without labels, we will have a mask of 0, and or meet this loss here. So we only supervise on those parts that there are labels. Okay, but this itself is not sufficient. So we would also have in today's words, because at that time people don't use contrastive learning yet. Okay, but actually what we are doing here, the Siamese loss, is similar to it's not to the extent of contrastive learning, because contrastive learning, besides the positive, you also divide by all the negatives, right, to normalize, to push it apart, right? But here, what we use is just a naive L2 divergence. Of course, you can also use KL divergence or things like this the minimum distance or other form of divergence to measure this. Okay, so we just use a L2 loss and we realize that it actually works pretty well, right? So it's just a Siamese loss. And then we also have a third branch, which is the inexact supervision branch. This is inspired by multi-instance label. Okay, so this is essentially a bag of labels, right? So because you have the very sparsely labeled, and you can actually propagate those labels to everywhere else, the neighbors. So you can actually group them together and then do a supervision by saying that every one of the whole bunch of it is actually, if they are similar in the features, then they should take the same labels. Okay, so this is what we call the multi-instance labeling here. And the fourth one, which is actually probably the most important one, that is some form of propagation. So when you look at semi-supervised learning, because semantic segmentation is essentially a classification task. Okay, so what you want to do here is that you can we introduce a smoothness loss. Okay, so basically this term over here is just saying that we form this weights over here, ij, is that because it's a point cloud, right? So we have a lot of points in the point cloud, and we form what we call the KNN tree. That means that for every point, I'm going to take the K nearest neighbor and add edges to it. So ij here would be the every edge in the KNN tree. Okay, and the way that we take the KNN tree, adding edges, is by spatial and color smoothness. That means that if they are spatially close to each other, K nearest neighbor spatially, we add the edges there. Okay. Of course, you can also have a fully connected graph, but the fully connected graph is expensive, right? So what you need to do is that then the computational complexity will increase. And then we also do, and so you use this as a weight. It's a weighted graph, right? So let's say between fxi and xj, you have xi and xj here. So the feature that we extracted, okay, the output, actually this is the output f here, is a feature over here, right, that we extracted. We want it to be, because we are minimizing this smoothness loss. So if they are very close to each other spatially, then ideally the feature should be the same. Because what we are saying here is that neighboring points, they are likely to take the same semantic labels, right? Because otherwise they are neighbors because of the reason, not because it's fated to be that way, right? It's because semantically they are most likely going to be related. And also we are also introducing a color smoothness. So that means that if they take the same color and the same spatial relation, then we would have W to be almost the same. So what we did, if you look at the paper in detail, what we did is that we compute this KNN graph twice, one for spatial, the other one for color. Then we have two weights, and we will take a average of it. We take the sum and then we take an average of it. Okay, and then the reason why we can take an average is because it's exponential. It's squeezed to become 0 and 1. Okay, and then we put it inside here, right? So what happens here is that in our paper we also show this, that you can actually evaluate this further, right? And what happens is that it's equivalent to label propagation in semi-supervised learning. So what happens here is that you have in semi-supervised learning, if I form this graph, KNN graph, right? Let's say I have a KNN graph where all the edges tells me either they are spatially related or semantically related. right? So if I have a label here, and I don't have the label for other points, then basically label propagation means that I can start from any unlabeled point, and then I take random walks. Okay, that means that I will do random walks. Let's say these are actually Markov matrix, because when you do this W, you can turn it into a Markov matrix to do random walks along the edges. Okay, so what happens here is that you can walk like a drunken man according to the Markov matrix. Then when you first end up to, well, you start at a point where you are unlabeled, but when you hit the first labeled node, you take that label. That's label propagation. Okay, and you can actually it ends up to be a eigenvector problem. Okay, eigenvalue problem that actually the way that we do PageRank algorithm is the same. It's actually it's conceptually the same thing. Okay, so yeah, so it turns out that this function here, you can be evaluated to that function. Okay, you can actually evaluate it and form a Laplacian matrix, and then you do random walk on it. Okay, so L0 norm simply means that we only count those, because W here it will be turned into 1 or 0. Okay, we are force it to become 1 or 0, and L0 norm means that we only count the total number of those entries with ones inside there. Okay, so with this smoothness constraint, then what happens here is that you are propagating the labels, okay, all the labeled data to the unlabeled features, to the unlabeled points. And therefore, at the end of this, all the 4 branches, they work together to actually turn it into a weak supervision 3D semantic segmentation. Okay, and of course, here's some results. We can even see that with 10% of the label points, we are almost equivalent to the fully supervised learning, or even some of them actually are even better. Okay, the reason is because it is largely due to this propagation, and also this kind of because we are doing something similar to contrastive learning at that time. Okay, it's self-training, right? So this branch here basically is a self-training branch. But now, of course, because you have to take that discount of 3 years, okay, that was in 2020. But now, of course, people look at contrastive learning is much more powerful than this. Okay, at that time we were still quite unaware. I don't know when was contrastive learning introduced. Probably also around that time, right? So, but now in today's term, you probably won't do this anymore. You will replace this with just contrastive learning. Right? It's much more powerful because you have you have a positive pair, and then you have all the negatives, and you try to do it. Right? So yeah, so this is quite effective, and here are some qualitative results. Right? So you can see that even 1 point supervision, right? We are almost close to the full supervision. And in fact, if you look at the comparison here, we might be actually better than the full supervision, even with just 1 point supervision. This shows that the self-training is actually good. It's actually excellent. I mean, I think that now you also have many follow-up works, okay, that are on this. I think recently there are also quite a few of the works that actually benchmark against us, because we also leave room for others when we did this. We didn't do it to the maximum. No, I'm just kidding. I mean, that's the best that we can do at that time. That's the reality. Okay, so yeah, I mean, and I think that now it gets a lot better because of all the more sophisticated techniques. Okay, so yeah, this is the semantic segmentation. Here's the part-based semantic segmentation. You can see that even 1 point, it looks visually quite good compared to the ground truth. All right, so any question on segmentation? If not, then I move on to the next task, which is the point cloud registration. So point cloud registration is also an interesting task in this for 3D point clouds. The idea here is that the task is this: given two point clouds, any pair of point clouds, right? It's defined in their own respective local frame. So respective local frame. So what you want to do is that you want to find what's the relative transformation, the rotation and translation, such that you register this. So let's say I find the registration of all this, okay, and then I can put it into the registered ones to form a room, for example, this whole scan of a room, okay, and of course, this the extension to this problem is rotation averaging, okay, as what we have mentioned in the global structure from motion case. But in this case, you don't have the translation ambiguity, okay, because the point cloud is with absolute scale, so there's no so there are some robust ways to do this where you can actually enforce low rank constraint, because rotation always is rank 3. So you can actually enforce a low rank constraint here. Okay, so the idea is, but what we are going to focus on in today's lecture is just a pair of point clouds. And here's some applications where you can use this, like for localization of autonomous vehicle. So there are actually 2 steps to the localization. The first step is that, because let's say you are given a very big map, the whole of Singapore, then you give a local query, right? You want to narrow down the search first before you find the post of the where it is. So you narrow down the search. In fact, I already talked about it. That's the place recognition, right? You treat it as a retriever, but after the retriever, basically you just get a very coarse localization. You know that it's roughly there, but you don't know what is the exact post with respect to the point cloud. So the point cloud registration would be the second step to do that, okay, to get the precise location. Contrast this to image-based retriever and post estimation. So we know PNP, effective endpoint algorithm. We learned this already in the lecture. We also saw vocabulary tree, the retriever. So let's say I give you the whole database of NUS. Okay, I have a map, or I geotag every image of NUS. That would be in my database. I might have millions of images there, right? And then I'm in one location. Let's say I'm in LT15 right now. I take a picture and I want to find out where is my exact location. Okay, or I have done structure for motion already using all the database. Now I take one picture and I want to find where am I inside that location. The first step is obviously not to do PNP, because to get that 2D, 3D correspondences, how are you going to search over the whole database? You have millions of images. That means that you could have hundreds of millions of key points, right? So that would be basically impossible or intractable to do. So the obvious choice is that you do a place recognition, a retriever. So that would be the vocabulary tree that we have learned, right? You do a retriever, or NetVLab actually, that can do that using deep learning. Then after you narrow down a coarse location, we do the 2D, 3D correspondence search and do PNP, right? So it's exactly the same idea here. So you do point cloud registration, point cloud retriever, then you do registration. So localization of autonomous vehicle can use this, and we can also do change detection from here, right? So if you have two, so if you traverse the same location, for example, you can see that there are basically 2 splitting image of the map. Okay, but what you really want is to align them like this. So this is, if I pass the same road here, by the way, this is one north. This is one part of one north that we actually took some data sets from there. Okay, so you can see that if you traverse over time over a very long period of time, some part of the scene has changed, and it's hard to register them together, right? So what you want to do is that you want to be able to do this registration such that it becomes like that, and then comparing once it's registered together, you can compare the two and detect all the changes in the scene. Okay, so we actually did a paper on this to do change detection in the scene, but the registration would be the first step. All right, so when we talk about registration, point cloud registration, we cannot don't mention this. Okay, the iterative closest point is the classic of the classic in point cloud registration. This is also called in short, the ICP. So the idea here is that given a source point and a reference point cloud, okay, what we want to do is that we want to find the rotation and translation that this is a rigid registration. That means that the point cloud doesn't move. Okay, internally it doesn't change. 3D FitNet is white baseline matching. This is iterative, some kind of iterative registration. Okay, so the idea here is this, that we have the rotation and translation over here, and so iteratively we'll do this starting from the beginning. Let's say the red points are here and the blue points are here. I'll find the closest points for every point in the reference. I'll find the closest point in the source. Okay, this can be done effectively by using the KD tree. Okay, you basically use a KD tree to search for the nearest neighbor, and then one iteration you find this the closest neighbor. Then you basically for every pair of the closest neighbor, you minimize the error, the point plus. So you have to rotate this source and into the reference, right? And then plus a t. So sorry, this should be minus. So essentially you want to minimize this error here, right? You transform this, rotate this point, you transform the source into the reference, and you minimize the error, total error. But you do this iteratively, right? Because we are just basing it on the nearest neighbor, right? So we do this iteratively. So after the next iteration, once you finish finding this, basically this is just solving the SVD. We actually talk about this, right? When we do the PMP, after you found the depth, we actually do this, right? So if you still remember, so but that's just one step because the correspondence here is just the nearest neighbor. So you iterate, if you move a little bit, and then you recalculate the nearest neighbor again. Then you do this minimization again, and you find the nearest neighbor again, iteratively until there's no more change in this error, or it stabilizes, right? Then you reach a local minima. So finally, it will look like this. But the main limitation is that it's susceptible to local minima. That means that what it means is that it has a very narrow range of convergence, a very narrow basin of convergence. This means that because it's iterative, it's susceptible to local minima. When you talk about local minima, let's say one dimensional, this is my global minima here. I have a local minima. If I start here, then I end up here instead of here, right? Because it's some sort of gradient descent. I will end up to get stuck in a local minima. So this means that the initialization needs to be close to the correct solution. It has a very narrow basin of convergence, right? So this is not good. That's where deep learning or learning from data can potentially help. Okay, so what we did here is that we proposed this RPM net. And by the way, there's also one problem with this is that if there is an outlier anywhere, then it might potentially also screw up everything. So we propose this RPM net, the robust point matching network. Okay, so basically it's based on RPM. There's a old work on called RPM. So what happens here is that we have a rigid source and reference. So we will predict we'll do some form of feature extraction first. Okay. Then we get for source we get fx, and for reference we get fy. Okay. The next step is that we compute a match matrix here. This match matrix can be seen as a assignment matrix. Okay. So basically, our assignment matrix is just a permutation matrix in the hard case. Okay. So this means that if you have, I believe that most of you here know what's the job assignment problem, right? You have n number of workers, n number of jobs. So only one worker can take one job. So that means that you can treat it as that you have n number of jobs here, and then n number of workers here. You want to assign each worker to one job, right? That means that the row and the column must sum up to 1. And every entry can be only 0 and 1. Okay, so this is a permutation matrix. But that's a hard assignment case. Soft assignment case means that it just needs to sum up to 1. Okay, and it need not necessarily be. So it just needs to sum up to 1, the row and the column. But every entry can be any number. Okay, the only constraint is that it needs to sum up to 1. Okay, so this is what we call the double stochastic matrix, in contrast to permutation matrix. So double stochastic matrix is also a Markov matrix, okay, because it sums to 1. Right? So it can be left-right stochastic, or it can be double stochastic. So in this case, it has to be a doubly stochastic matrix. Okay, and what's interesting here is that if it is a hard assignment, then it's not differentiable. But fortunately, there's something called a synchron layer or synchron matrix. Synchron matrix. So what it says is this. Synchron, I just briefly give you the idea. Synchron matrix or synchron layer says this, right? If I start off with a matrix that has positive numbers inside there, and then I keep on normalizing the rows and columns, I keep on iteratively normalizing it. Eventually, it will settle down to become the double stochastic matrix. Okay, and this process is actually differentiable. So that means that the synchron layer can double up as my matching matrix or my permutation matrix in a relaxed form. Okay, and therefore we introduce this. There are two. So the two main components is that first we use this feature, this PPF net feature. This is a local feature. So we do FPS to select all the further sample points, and then we take the centroid and compute all the delta x1z. Okay, and then we compute the angle between the normal and between every one of this delta xyz. Okay, so this will form the PPF. It's actually in this paper here. Okay, so this is good for local features because it's taking locally the geometrical structure into account. So it actually captures that essence of it, right? So once you have this, then we would have the feature. And the next thing is actually to compute the match matrix. As I mentioned, what we want is a doubly stochastic matrix. That means that it just needs to sum up to 1, the rows and the rows and columns. Okay, so so what happens here is that you can start off with computing the distance, okay, and then put it into a synchron layer because the distance here is always positive, right? So it eventually will evolve into summing up, everything summing up to 1 that looks like this. Okay, so the good assignment means that there won't be conflict between the row and column. It becomes a doubly stochastic matrix. if you take the maximum and just put it as 1, and all the rest putting it as 0, then you would see a permutation matrix occurring. Okay, so this is a good assignment, and this is our objective. We want it to be like that, right? So, but and what happens here is that this can be done using a syncon layer. So basically, the score inside here can be exponential negative of the distance, so that you know that it's always going to be more than 0 and equals or to be 0 to 1. Okay, so there is a weight here that we need to learn. We set it as a learning parameter in the deep network, such that when you evolve through the syncon layer, eventually it will give you something like this, the doubly stochastic matrix. Okay, but what happens here is that some points, they might not have correspondences. Okay, because it's not always equal number on both sides. Okay, and it might also be outliers. So the idea here is that we create a dustbin column and dustbin row. Okay, or we call it the slack column or slack row, such that anything that cannot be assigned to the rows and columns here in the main part, we can dump it inside the slack column or slack row, such that the constraint, it can still be put into the syncon layer, such that the constraint will still sum up to 1. But now what happens is that it need not necessarily be the main portion of this summing up to 1 anymore. Right? So you can actually push everything to the slack column and let all the rest becomes 0. But there might be a degeneracy here. So everything can get dumped into the dustbin column or dustbin row. So there's a threshold here. That's why there's a threshold here to prevent. And that threshold, we also don't set it as hyperparameters. We learn it. We use we just dump it inside there and define a loss on it and let it learn. Okay, so this is the way that we make it robust, such that it allows for outliers to occur, but it's still able to do it. Okay, and interestingly, this is how it looks like when there's a toilet bowl actually. Then the table. If you compare with ICP and all this, you can see that our error is much lower. We are not the first work in this. Like RPN is the original one, and we compare, we actually beat it by quite a fair bit because it's data driven. We're actually learning the features. Right? So it's actually kind of interesting here. Right? And PointNet LK and DCP V2, these are deep learning methods. We're not the first to do this. But at that time, we actually beat them. And actually, this is also not the latest work that we have. We also have another one, but I didn't include this. That was Zijian's last work before he defended his thesis. That was at CVPR last year. We call it Regtr, REGTR. Okay, it sounds similar to ether. Okay, as you guess, it's actually transformer inside there. So it's actually a very, very simple thing, because we thought that the transformer with self-attention and cross-attention can actually capture both the internal, because you have a source and a reference point cloud. The self-attention will capture for every point, it will capture its relation with every other point in that respective point cloud, and the other one as well. That because you are doing registration, so the cross attention here will matter a lot, right? So what happens here is that instead of doing, in this case here, we are doing matching. We are doing matching explicitly here. We have a match matrix. This is something like an assignment matrix. But in Regtr, what we do here is that for the source point cloud, because each one of them comes with a reference to its own reference frame. So what we do here is that we directly predict how the source point cloud would transform into the reference. and then how the reference would transform into the source point cloud. Okay, using just the transformer, and it actually works very well there. Okay, that was actually the last work of Zen before he graduates, and that was published last year in CVPR. Okay, and yeah, so these are the works that we have done in the registration, and then finally so you can also see that the weights here, the reference weights here, it tells you something. Okay, it actually when we visualize the weights on the reference and source, we can see that it's actually the parts where they overlap gives the highest weight. Okay, which it should be true, because this is where fx is assigned to fy as a match. Okay, when it's assigned to fy and fx as a match, then there must be an overlap, right? That's why when you visualize the weights, there's no surprise that it shows up as at the overlapping point. Okay, so this is quite intuitive here. Okay, any question on the registration, point cloud registration? So this is also one big task in 3D point cloud. Okay. The point cloud registration. Then the last thing that I want to talk about is also registration. But you might find this slide familiar. Okay. So this slide here is this slide is actually from our lecture slide, okay, PMP. So the idea here is that when we do perspective and post, we want to, given the 3D, 2D correspondence here, we want to find what is the 3D points is defined with respect to a world frame, but the image is defined with respect to a camera frame. So given the 2D, 3D correspondences here, we want to find what is the rotation and translation that register this. Okay, that in the camera pose with respect to the world frame. And this involves two different modalities. I recall that during the lecture, someone actually asked me, how do we, or actually before this lecture, someone actually asked me, how do we, when you have the 3D point clouds, how do you actually register this or check that the 2D, 3D is actually a correspondence? So usually what we do in structure for motion is that we will store all the SIF or surf key points into the 3D points. Then in the image, we will extract the same key points and then we will match it, right? But this is actually not that robust. Okay, the thing is that if you have a drastic change in the appearance, then it becomes difficult. So this comes back to the same problem as the place recognition. I mentioned that if I have day and night, place recognition is difficult. This 2D, 3D key point correspondence search is even more difficult. Right? So the thing is that, let's say I have my map that is taken that is built in the daytime. Let's say I go out in the 3 p.m. in the afternoon to map out the thing. I do structure for motion, and I build this key points with the descriptor in the afternoon. But at night, I go into the same route again, or even heavy rain, without rain, sunny, cloudy, right? So the 2D key points that I'm extracting here, the SIF features, it might not match because there's appearance change already, right? So that is the key challenge here. And it's very difficult to learn this because again, it's also because of the data limitation. You don't know how to label it. And then also at the same time, you don't have so many data or so much data that to capture the variation. Yeah. So anyways, this is difficult, right? So this is known as the PMP problem. And so this triggers me to think about, or triggers us to think about at some point of time. I actually also wrote this in my PhD future work. That 10 years ago, I wrote this inside there. And then it took quite a while before we came out with this. So the thing is that the question is this: whether we can establish the 2D, 3D correspondences, right, directly using point cloud. Let's say my point cloud is built based on laser sensor. That originally or inherently, there's no such thing as descriptors or safe descriptors anymore, because I don't no longer build that point cloud from images. And as I've mentioned or motivated earlier, that 3D point clouds or the models, the digital models that is constructed from LiDAR lasers are actually much more accurate. So why don't we just use that map as a reference map, right? But then the problem here is that now we live in two different modalities. So the advantage of LiDAR is that it's very accurate, but the disadvantage of it is high maintenance because there's rotating parts. Anything that's rotating is no good. It's hard to maintain. It breaks down. Sorry? Yes, it breaks down very easily. Contrast this with your camera. So like this camera over here, no matter how I break it or I drop it, it still works. Right? So the thing is that and it's also cheap, much cheaper. LiDAR Velo 964 cost about 70,000 USD. Camera like this cost about, I don't know, like $100, 100 Singapore dollars. Okay, probably less than 100 USD. So then it actually makes more sense to use LiDAR for the acquisition of large-scale model, digital model, because it's more accurate. But for the deployment, right, you just need one LiDAR to do that mapping. But for the deployment, you have the reference map already, very accurate reference map that is gotten by your obtained by your very expensive LiDAR once. Then your deployment, you can send out all your autonomous vehicles, right? You have many of those. Let's say you have a whole fleet of taxi or a whole fleet of self-driving buses mounted. You don't mount every one of those with a 60 or 70,000 USD LiDAR sensor that's so hard to maintain. The obvious choice is that you mount camera on it, right? So now, then it comes the question of, there is a cross-modality challenge here. How to establish the 2D, 3D correspondences, right? So that if you cannot do this, the next step here, which we have learned, will fail badly, okay? Because wrong correspondence means that nothing can be computed anymore, right? So we actually did also the first work on this, that we thought that we just use, at that time it was triplet loss, the triplet network. So we thought that we just register, because this data set here has LiDAR and cameras calibrated, is mounted rigidly on the car. So according to that transformation, the calibration, we will know how to back project the 3D LiDAR points onto the image. And then what happens here is that we can extract the image key points. Okay, we can extract the image key points and find the corresponding ones on the 3D point cloud. So basically the 3D point cloud will use IFS or whatever key point detector, our 3D FitNet. And then the 2D ones we use SIP, and we try to minimize we try to do some sort of triplet loss, okay, to learn a new descriptor that can work across modality, okay. But the problem with this is that although we show the initial work here, this was the first work to actually show this, okay, and the matching count is quite low here because we are inherently living in two modality. What happens here is that we twist the idea a little bit. Instead of doing 2D, 3D matches here, because they live in different modality. So why you force them together, right? So now we are going to say this. Each camera here, we would have a custom of the camera. We know where which points are in the view of the camera. They are projected into the camera. So instead of learning the descriptors across modality, we twist the problem to become this. We just twist the problem to become that given a set of point cloud, we want to do a 1-0 binary labeling. Okay? If it is 1, that is in the view of the camera. If it is 0, then it's not in the view of the camera. Okay, so as simple as that. Okay, then it becomes a classification problem in the first. So once you give, that means that I give the point cloud and I give the camera image at the same time. So we would have to design a network that fuses the two modality in terms of features, but you will output for every point a label of 1 or 0, whether is it inside the view of the camera or outside the view of the camera. Okay, then once we have this, okay, so we design a optimization. So this is just a Gauss-Newton solver, but in contrast to what we have learned in bundle adjustment, that we minimize the reprojection error. Now we formulate this such that if you are having a camera, you know where are the points that should be inside the view of the camera, but you don't know what is the pose of the camera with respect to the point cloud. So what we want to optimize is that we want to optimize for the pose, such that when we do an optimization, the cost function is that we want to move the camera such that all those points that are labeled 1 should be reprojected back onto the image as much as possible. So that becomes our cost function. Okay, this is the 2 steps. Of course, it's not so trivial. We did a lot of, we actually need to use the exponential map and the logarithmic map. Actually, all these are taught in class. Okay, so all these are actually taught in class. And okay, so the point classification would be simple. We'll just let it be every point, we'll take LNC over here, it will be inside 0 or 1. Okay, so it's either inside or outside. Then this is a network. We have a point cloud encoder and also a image encoder. Then we do attention fusion here. So this is the fusion. We just attention fusion. But nowadays, if you want to do this, right, I guess you do it using transformer, right? So you have a point cloud encoder. Actually, you can just use the VIT as well. VIT works for image 16 by 16 patches. Point cloud, you can do the same too. You can actually cluster it. You can do a FPS, right, and make it into 16 clusters or whatever. Then, no, you make it into 16 by 16 clusters. Okay, then you dump it inside the transformer. 2 different sets of tokens, and then it will output whatever stuff that you want, the features. Right. So if in today's context, that will be what we should be doing. Okay, but this was published 2019. Then we put it inside a decoder, and where this will just simply be a binary classification, 1 or 0. Okay, and so once we know this 1 or 0 label, given the point cloud 1 or 0, we design an optimization algorithm to find out the pose. So this would be the cost function, okay, optimal pose. So there are 2 terms to it. One of it is that we want to shift everything such that we want to shift the pose G over here, such that if the points are inside the viewpoint, okay, then it would be 1. If it is outside the viewpoint, when we shift this thing, the reprojection, if the point is inside, we will give it 1. If it is outside, then we will give it 0. So 0.5 here, right? And then the other part here is that we want to take the label, every point that is the label that we have seen, okay, that is given by the network, and minus it by 0.5. Okay, and then what happens here is that if you maximize this term over here, right? So what you want to, because these terms here, if it is wrong, okay, if it is wrong, it could be minus. It becomes negative. And this term here, if it is wrong, it will also be negative. So there is only one combination where both must be right. Then it's positive. Then you maximize it. Right? So we want to optimize it over G, the pose, such that these terms here, when you multiply together, they must all be positive. They must be all maximizing it. Okay, and this we turn this into an unconstrained optimization, but the derivation is kind of complicated. So I omitted all the details. If you are interested, you look at the paper. Okay. And you should be able to understand by now, actually. I hope so. So yeah, so and you can easily use a Gauss-Newton solver to do it. Okay, so this is just an idea here. You can see that the custom of this, the labeled points is in green. Okay, so the network can predict pretty well the labeled points. Then as the Gauss-Newton optimizes from 0, we do 3 checkpoints over here. So 0, 40, and 80. 0, 40, 80 iteration. So you can see that it gradually moves towards the correct host, such that the whole labeled points is inside the viewpoint of the camera. Okay, then we know that we find the correct host here. We cleverly just make use of deep learning to give us 1, 0, but all the rest are still done in the correct way of optimization and mathematics. Right, so this is the thing that I think that we should be looking at in this way, because it doesn't make sense to dump everything into a deep network and treat it like a black box. Okay, including like just now the RPMNet, you can see that the Singhorn layer, that is a relation, is actually doing the assignment matrix. Okay, so these are the things that we try to do. Okay, any questions so far? If not, then I guess I'm at the end of the lecture already. So we compare with, because we are the first method to actually do this. So here's some comparison. Although it's not perfect, there's still a large room to improve this. Right. So this is nonetheless this is a cool idea that that we thought of, and here's some results that after the correct optimization. Okay, so any question? If no question, then that's it for today's lecture. So in summary, I talk about implicit, explicit surface. I'll talk more about this next week. And then I talk about the representation of point cloud and how deep learning can be used for point cloud representation. And finally, I talk about the 6 different tasks of point cloud. But note that it's not limited to these 60 different tasks. There are more other tasks like point cloud completion, scene flow, and things like this that I didn't talk about. Okay, so yeah, that's it for today's lecture. I'll see everyone again next week for the last lecture, and I'll talk about neural fields representation. Okay, thank you.